I know.
Yeah, this is why I think my life is complicated.
Oh, no.
Actually, no, this is why I know.
I know. Eventually.
So different from ours.
And the reason my phone isn't working is the materials lab, like concrete.
Like what? Right in.
Right in the mixer. Because it was in my pocket.
How did it?
It was in my pocket and I bent over and it just all the way in, right in the phone.
How did you start? Like, how
I don't.
There is.
Okay.
I have to drop my phone in concrete because I'm a civil engineering major. So how else would you break your phone?
I mean, I know in one of my interviews. Dropped his phone the same way. He really just pulled it out of his pocket and threw it across the river and then just never got the phone back.
Yes.
It has concrete in the ringer, but luckily my ringer is stuck on off. So not stuck on on, it's stuck on off. And then the speaker has concrete in it. I think I got most of it out of the charging port. It does charge.
That's a good thing.
Um,
Screwed up.
It's got some, the case is more or less stuck to my phone. But
Sound check? And hear us? Good. All right. Are there any questions before we start from either the class or people online? Yeah. All right. So not hearing any questions, everybody should have their handout on energy. And basically the first couple slides in today's presentation, I just cut and paste right from that handout. The derivation is in your textbook. And again, I don't hold you to derivations. You need to understand when you're using the equations, when you violate those assumptions to the derivations, because then the equations may not work so well, if at all. So we want to develop the second law of fluid mechanics. The first law we talked about was continuity. We'll do energy, have some fun with that, and then we'll move on to momentum. So as before, we're going to use the same coordinate axis system. Vertical is upwards z, and that dimension is collinear with the acceleration due to gravity. X and Y are horizontal coordinates. They are shown as being orthogonal. It's not an absolute necessity. Sometimes in groundwater flow, when we're looking at fractured rock, the X, Y, and Z directions, we actually align with the rock fractures. And they're not only necessarily looking like this, but they may also not have 90 degrees between them. But again, it just helps us with the flow domain compared to where the rock is, the no flow domain. So typically when you assign the coordinate axis system and even you look at a little differential cube like we will, ultimately that falls out of the derivation. So the acceleration field we had before, we're only considering the acceleration due to gravity, okay? There's no other accelerations, no AX, no AZ. So again, only gravity. Oops. No other extraneous acceleration fields. And we're going to start exactly what we did before with fluid statics. We're going to start with a little cube. which is differential in size, dx by dz by dy being into and out of your paper or into and out of the board, into and out of the slide. And again, since gravity is collinear with the z direction, basically we could look at a two-dimensional derivation. The x is what happens in the y, but in this case, I'm going to look at all three directions, and you'll see that. So again, what we're assuming is fundamentally, as we did before with fluid statics, as we did before with acceleration of finite fluid masses, we're going to have pressure varying with space. When we looked at acceleration of fluid masses, we had this term, which was the acceleration field times the mass. Again, no other accelerations other than gravity. How does gravity manifest itself? Through weight. Okay. Again, I cropped these from the other derivation on acceleration of fluid masses just to show you we're basically doing the same thing, only now we're taking off the acceleration field and all of the components associated with it. And then likewise in the z direction, we can start at one location at z. As we move across to the top of this element, we're going to see that by moving through space, a distance dz, we've changed the pressure because we're assuming that there's this pressure gradient in the z direction. So again, basically, as we did before with fluid statics, we're just saying that we may know the physical distances we moved, dx, dy, dz, but we're trying to figure out how the pressure was changed due to this. The other thing that's happening is this is now in a flow field. We have this could be a little differential cube inside of a pipe. And flow is moving actually through this cube, and you're looking at this snapshot in time. And so what we're going to see is before when we looked at this and it was static, we had our old friends dp dx is 0, dp dz is minus gamma. But now because of this, the fact that we have velocity or kinetic energy, that's going to affect these pressure gradients, as you will see. So we start with Newton's second law, and that is that the sum of the forces in any direction is mass times acceleration. And we can look at mass times acceleration as the time rate of change of linear momentum, which is kind of convenient. So basically, this sum of the forces would be the pressures acting all over the surfaces. It would be the weight. Those are known as body forces. Ma is the mass times acceleration of the little cube, dx, dy, dz. And a way to represent that mass times acceleration is basically the change in linear momentum from where this flux is entering to where it's leaving. And actually, that's what we're going to do when we talk about momentum. So again, all we're saying is that the sum of the forces, the time rate of change of linear momentum for the fluid. And we also want to recognize that whenever you see this capital V with the little arrow over the top of it, that's the velocity vector, just like A was the acceleration vector before when we looked at finite fluid masses subjected to acceleration. So the velocity vector has components collinear with the x, y, and z direction. In this derivation, I use Vx, Vy, dz. In many other derivations, the x component is u, the y component is little v, and the z component is little w. So don't be confused when you may even see that in your textbook, but it's very common. And so what we can then do is look at some assumptions for this derivation. One is that, again, as I've said, only gravity is the acceleration field, and it's collinear with the z direction, and it is occurring in the negative z direction. And just like before, when we looked at fluid statics or even finite fluid volumes subjected to acceleration, we're going to account for the fact that the weight is acting in the negative z. And so we've already counted for which way gravity is occurring. The second assumption is that the flow is inviscid. So this is why we make that assumption. if we apply Newton's second law, sum of the forces in the x direction is equal to the time rate of change of linear momentum. Again, F1 is due to the pressure distribution on the left side of the cube. F2 is due to the pressure distribution on the right side of the cube. If we have viscosity and you have velocity changing within the cube, and you will actually be measuring this in one of your labs, that velocity does change the further and further away you get from a wall of a pipe. Then you would necessarily have shear stresses on all over the surfaces. I've just drawn the ones in the x direction that are on, this is on the dx dy face. So this is the shear on the dx dy face. And the one on the bottom is also the shear on the bottom on the dx dy face. But on the side you're looking at, which is the dz dx face, if there was another cube right in front of it, and those cubes are moving at different velocities, there's also a shear on that face acting in this direction. And on the back side of the cube, there's also a shear on that face, on the dz dx face. So when we say we have an inviscid fluid, first quiz of the day, zoomies versus face-to-face. Have you ever seen that equation before? What equation is that?
Viscosity.
Yeah,
Well, it's for like, objects going past like objects that are moving, going past objects that are still.
when you have differences in velocity throughout a fluid, this was Newton's law of viscosity. And the shear stress is equal to the viscosity times the velocity gradient. There were two problems on exam 1 that used this. So by saying we have an inviscid fluid, we're saying that the viscosity is 0. And therefore, none of the shear stresses that I just drew on all these faces exists. That makes the sum of the forces term easy. Is this realistic? Of course not. But we're walking before we're running. After we get through energy and momentum, then we're going to go back and say, okay, what happens if we do have viscosity? And what this ultimately leads us to is energy losses due to frictional resistance. Okay, so right now we're basically saying we have frictionless flow. Think of if you've ever played table hockey, where you have a little puck and the air is keeping it buoyed above the surface of the table, and you just tap that puck and it can just keep moving around at almost for a very long time, at almost an inviscid flow in that case, or an inviscid movement, frictionless movement. So that's the second assumption. The third assumption is that our little box has a constant size. There are two ways of doing analyses. One where the box has a constant size and you look at the fluid flow through it. It's called an Eulerian system. Or the other where you have this box and you follow the box and it can change shape as you move. That's called the Lagrangian conceptual system. And both of those ways of looking at this, you'll get to the same end result. But in this case, we're just saying that it's got a fixed size and we're looking at the fluid as it moves through it. We're going to assume that we have an incompressible fluid, that the density is equal to 0. Obviously, that tailors this derivation towards liquids. Most liquids we can assume to be incompressible. Gases at low velocities also somewhat satisfy this. So again, the movement of the air through the ductwork in this building is almost a constant pressure system. It only changes once you get close to the pumps that are moving the air around. The element weight, again, is on a differential scale, the specific weight, which is density times acceleration due to gravity, times volume. And by now, you should know what that is, gamma V. And then the elemental mass is just density times, again, the same volume, dx dy dz. So these are all the assumptions, and we'll revisit those after we get through this. So what we do then is apply Newton's second law in each direction, the x, the y, and the z direction. So what we would say to start off is that the sum of the forces in the x direction is equal to the time rate of change of linear momentum in the x direction, mvx. And when we expand the sum of the forces, remember, if this is our box, our little cube, which is dx by dz, we had a pressure px on this side, and the pressure on this side was px plus dp dx. And then it acts over the area, the end area of this cube is dy into the board times dz. This pressure also acts over dy dz. And so that's where these two terms come from. That's the force on the left, which on the last slide I called F1, and the force on the right on this last slide I called F2. This is exactly what we did for fluid statics. It's exactly what we did for finite fluid volumes subjected to acceleration. You can see in the y direction, it looks very similar. Really, the only difference is the subscript y instead of x. And in the z direction, again, the big difference is that weight acts in the z direction. So again, on the bottom of this cube, this was pz, and so this might be the force on the bottom. Let's call that F3. On the top, we had a pressure distribution, call that F4, and then we had the weight dW. So this is F3 acting upward. This is F4 acting downward. And this is the weight also acting downward, hence the positive and negative signs in front of each of those forces. And then I think you can see this term minus P of x plus dP dx dx times the same area, these first two terms are going to cancel. And that's what you'll see in the next slide. So in the next slide, all we do is reduce it. And what it says is that the time rate of change of linear momentum in any direction is equal to, again, what's on the right-hand side, all the way on the right, are forces. However, what we've done is reduce them, one, by getting rid of the things we could cancel out, but two, we divided both sides of the equation by the volume of the cube, dx dy dz. So you don't see the volume of the cube in there anymore. So instead of the mass, which was rho dx dy dz, that canceled out. So the only thing you see as a difference here is they all look the same except for the z direction. We have this minus gamma or minus rho g term. Again, these are all cropped right from your handout. So if we take that last equation, which is a component, there's one equation for the x, one for the y, one for the z, and we put it into one single vector equation. What we would say is the time rate of change of linear momentum, which is rho, and now that velocity on the left-hand side is the entire velocity vector, which is again, the velocity vector in the x plus the velocity vector in the y plus the velocity vector in the z, and those are vector sums. So you're summing those three together. And that's equal to, the negative sign came from the fact that there was a negative in front of all of those dp dx, dp dy, dp dz terms. That's called the gradient. So grad p is equal to dp dx plus dp dy plus dp dz. And then from the z direction, in order to make this into the vector sum, since gravity and weight only was acting in the z direction, we had in the last form of this in the z direction a minus rho g, or a minus gamma. All we did was multiply by the unit vector in the z direction. Remember from statics, ijk. So this is just k is the unit vector in the z direction. And that just tells you that in this vector, one simple vector equation, that's only operating in the z. And then another way to actually, what we would like to do is pull this into that gradient operator. And how we do that is instead of using the unit vector, we're just going to use some distance in the z direction. And so obviously by pulling it into the gradient term, remember, gradient of rho gz in this case is equal to d dx of rho gz plus d dy of rho gz plus d dz of rho gz. And in this case, rho g is a constant. It can be pulled out of all of those. What is dz dx? Well, what is that asking you? If I move in the x direction, what's the change in z? Sure. What is dz? Dz dy, sorry. Same thing. If I move in just the y direction, what's my change in z? It's 0. And in the last one, ddz of rho gz is just rho g. It gets us back to this term. So again, that's a sneaky way of pulling the weight into this gradient operator, again, just to get us a very simple vector equation. So now what we would like to do is explore the left-hand side a little bit. We can divide the entire equation by density. And so if we divide by density, obviously we'll cancel out the density here. We'll cancel out the density on the rho g z term, and we'll have a p over density term. And this form of the equation is known as Euler's equation. Probably butchering that pronunciation, but if you start to look at journal articles and you're trying to look for something that applies to something you're designing, they may say, I'm going to start here and then run off, and then they'll come up with some design equations. So they don't go back to square one and rederive everything. They just start right here. So starting with this Euler equation, and looking at the left-hand side. So I'm going to go back a little bit. We just want to look at this left-hand side. That left-hand side, d dt of the velocity vector, is the total derivative of the velocity vector. So just like we're assuming with pressure, we're assuming changes with x, y, and z in time. Velocity can also vary with x, y, and z in time. And so when you take this derivative, it's equal to the sum of the partial derivatives with respect to each component independent variable. So what that means is when we take that total derivative of velocity vector with respect to time, that's the derivative of the velocity vector with respect to time, dt dt, derivative of the velocity vector with respect to x, dx dt. So again, this is the direction you're looking at when you're taking the partial derivative, and that dt is this guy. So we've expanded that out, and when we expand that out, again, for example, if you look at this term, this is the partial derivative of the total velocity vector with respect to x. And so that's d dx of dx plus vy plus vz. And again, capital V is the total velocity vector. It's equal to those sum of those three compounds. And when we look at d dx, the partial derivative with respect to x of vx plus vy plus vz, the only one that's going to remain is vx, because vy is not a function of x and vz is not a function of x. So dv dx is dvx dx, dv dy is dvy dy, and dvz is equal to dvz dz. So we're going to substitute all of these back into this equation. And when we do that, we're also going to recognize that dx dt is the velocity component in the x direction. dy dt is the velocity component in the y direction. and dz dt is the velocity component in the z direction. And that's discussing the second term in each of the last three terms. So that's another substitution we're going to put in here. So for example, this first term, dv dx dx dt, when we make these two substitutions, is going to be dvx dx, that's this substitution, times vx. That's this substitution. Or vx dvx dx. And so those how we're going to make all the substitutions, and that gives us equation 13 in your handout, where each of these terms is now only with their respective component in their respective direction. These three terms are known as convective accelerations. This one is known as normal or local acceleration. Normal or local acceleration. What does this mean? It means if I go from this point and I move just in the x in this point, the velocity changed. Does that happen in real life? Have you ever seen a stream? You have locations of shallow water moving very fast and locations of deeper water moving very slow. That's the change in the velocity vector as you're moving in the x direction. It's subscribing to the continuity equation. Q is equal to VA. Same discharge, but as you change the cross-sectional area, velocity changes. So these are all convective accelerations. What's this one? It's a local or normal acceleration. What does that mean? The first three, the convective accelerations, we're talking about take a snapshot in time and tell me how the velocity changes as you move through space. This one is saying, look at one location and tell me what happens with the velocity vector at that one location. So if you have what's called steady flow, you have one velocity at this location, and that's happening now. It's happening 10 minutes from now. It's happening 10 years from now. Steady flow means the velocity is constant, or the discharge is constant at that location. If you have unsteady flow, think of a dam break. You're fishing by the side of the river. You're at one location, and what you see is this big flood wave coming downstream. The water surface rises up because the discharge is changing, and therefore the velocity is changing. So local acceleration, convective acceleration. And that's what the total time derivative of the velocity vector is. It has these two components. So let's just focus on the x direction. And this is equation 14 from your handout. In this x direction, what we now have is this the right-hand side is from the gradient operator. And again, there were two components in the gradient operator. There was a pressure component and this elevation component. And I know that dz dx is 0, but I just want to keep this component in there. I could do this for any direction. I just chose the x. And on the left-hand side, we have the two components that came from the total derivative of the velocity vector. We have a local acceleration, or an unsteady component, and we have a convective acceleration component. The left-hand side came from mass times acceleration. The right-hand side came from sum of forces. But we're so far from that, it's hard to recognize it as such, but that's where they all came from. So let's assume, and that's what we're going to do in this course, that we have steady flow. In more advanced courses in this program, we relax that and we look at unsteady flow. For example, dam breaks or surges in pipelines. But for this course, we're going to look at steady flow. And when we do that, that means that term is 0. So when we look at steady flow, we lose that first term. And the other thing you'll see is Before we had an equation where Vx, dVx, dx was on the left-hand side, and you'll see in equation 15, we basically brought all the terms on the right-hand side to the left-hand side, which means the right-hand side is now 0. So these two terms that had negative signs in front of them were brought to the left-hand side of the equation with Vx, dVx, dx. And the other thing that you will see is we divided the entire equation by the acceleration due to gravity. And so all of a sudden, Vx over g appeared. 1 over rho became 1 over rho g. And the g in dz dx is now gone. We're getting really close now. So I want to look at the leftmost term, the convective acceleration term. And bear with me. You know that the derivative of a product is the derivative of the first times the second plus the second times the derivative of the first. So the derivative of v squared is the derivative of a product, v times v. Happens to be the same number, but it's a product. So this is the first times the derivative of the second, and the second times the derivative of the first. So the derivative of v squared dx is 2v v over 2v dv dx. And over here, we just see 1 dv dx. And so this term is equal to 1 over 2g dv squared x dx. Okay. So we're just going to make that substitution. And so here's that substitution we just talked about. And lo and behold, everything is with respect to ddx. So let's pull the operator outside, and everything else is on the inside. If ddx of vx squared over 2g plus p over gamma plus z is 0, what must this be? If the derivative of something is 0, what must that something be?
Constant.
That'd be a constant, right? This is like your first calculus course. Yeah, that's absolutely correct. So v squared over 2g plus p over gamma plus z is a constant, and we call that constant the Bernoulli sum, capital B. All right. This is basically the fundamental of the energy equation. Capital B is the Bernoulli sum. Let's go back. What are the dimensions of elevation? Anybody online know that answer? Because everybody in the class is stuck. Yeah.
Any length, like feet? inches?
Length, feet, meters, centimeters, millimeters, cubits, length. You're adding z to p over gamma. What are the dimensions of p over gamma? Length, right? You know that from fluid statics. What are the dimensions of v squared over 2g? I'm going out on a limb now. What do you think the dimensions of v squared over 2g are? Length. This equation is dimensionally consistent. So it's odd to be thinking of energy as having the dimensions of length. It's actually a little more complicated than that, but for this course, that's how we're going to leave it. So B is the Bernoulli sum. It's also known as the total energy, or the total energy head as it's known. V squared over 2g is kinetic energy, or known as the velocity head. The velocity in that v squared over 2g term is the average fluid velocity. And so we typically get that by discharge divided by area. So for example, if you're talking about a pipe, we're going to have some discharge, it's going to have a cross-sectional area, A. And so the average velocity, again, what we say is you basically have this average velocity across the cross-section. We know it's not constant. But what goes into the energy equation is the average velocity for the cross-section. P over gamma is the potential energy. And I don't even know why I have held in there. I'm making these up before class as usual. Potential energy as pressure or as pressure head, L. Meaning it's got the dimensions of length. And Z is also potential energy. Physically, it's the elevation of the fluid particle. So a fluid particle sitting higher than another one has more potential energy than the one smaller than it. And that has everything to do with the Z-axis being upwards positive. Elevation. So here's a little pipe with a piezometer in it. And at this point, we would be describing the elevation of that point. That's the number that would go into the Bernoulli equation. If you wanted to know the total energy of that point, you need to know V squared over 2G at that point, P over gamma at that point, and Z. Z is physically the elevation, and right here we're focusing on the center line of the pipe. Same figure. We have a pressure at the center line of the pipe. You know from a few of your labs now that we can represent pressure as a column of fluid. We did this with fluid statics. And we used this manometer, and the distance that that column of fluid would rise above the center line of the pipe is P over gamma. That's the same term that appears in the Bernoulli sum. And again, the manometer could be off to the side. So here we have fluid flowing in the pipe, but there's no flow in the manometer. It's giving you a static reading. This manometer is no different than if you just had a pressure gauge on the side of the pipe. So in the Bernoulli equation, or the energy equation, that P over gamma term, a manometer could be giving you the pressure, or just a pressure gauge could be giving you that pressure. When you look at future labs that you'll be having, you'll see that we use pressure gauges throughout the system. And that's what we use in real pressure transmission systems. We use pressure gauges everywhere because they help us understand how energy is being distributed throughout the system. And that's the name of the game, is trying to maximize your energy and minimizing losses in the systems. So you saw this in the open channel flume, but we use what's called a pitot gauge. And if you ever fly again, if that even's going to happen, just below the cockpit, you will see a pitot tube sticking out of the airplane. And that helps us measure velocity. How? If this is the manometer, it's measuring P over gamma. A pitot tube measures V squared over 2G plus P over gamma. Outside of the plane, what's the pressure? What's the pressure in this room?
Atmospheric.
Atmospheric. So if you have this pitot tube sticking out of the plane and P over gamma is 0 because it's atmospheric, that pitot tube is giving you directly V squared over 2G. And instead of a gauge, that pitot tube, instead of a manometer or a column of fluid, it could just be reading on a gauge. And I'll bring one of those in next class. And so that gauge, you could actually have the dimension in feet, and then you would have to take that dimension in feet, multiply it by 2G and take the square root, and you would get your velocity, or they would just create a scale that already does that for you, and you read velocity right off the scale, which is more common. So pitot tube is one way to measure velocity, and there's other ways we're going to be talking about them. But these are just, again, the individual components we're talking about. So way back when, we went over these assumptions, and I just want to remind you of them. One is that you have a fluid continuum. What does that mean? We did this derivation, and it assumes that you can draw a path from one point to another. If you can't do that, you don't have a continuum. Now, I know it's obvious. You have a pipe here and a glass of water over here, and they're separated. That's not a continuum. There's no way you can draw a path line into that glass. But in pressure piping systems, you could have some valves closed that you don't know about. So you think you have a continuum, but you really don't. And in that case, you might be trying to apply the equations. You don't understand why the data isn't telling you what the equations are telling you. So it's typically not obvious that you don't have a continuum until you do more probing of the system. The density is constant, steady flow, only acceleration field is gravity, inviscid fluid, so no shear stresses, and that we had a constant cube of dx dy dz, and flow is moving through this fixed grid system. So let's ask this simple question. What if the fluid were not moving? It's static. Well, if it's static, then the velocity is 0, right? So your Bernoulli sum is just P over gamma plus Z. That's fluid statics. This is a slide right from our fluid statics derivation in our fluid statics lectures. Here we have a free surface, and it's a static fluid. And we would like to understand the relationship between pressures and elevations in this fluid. For example, between point 1 and point 2. So here is the derived version of the fluid statics equation. Separate variables, open integration. When we do the open integration, you have pressures on one side, elevations on the other, and rearrange similar subscripts. This is exactly what was on the last slide. So our general energy equation recognizes that fluid statics is just a subset of the more overall description of energy in systems. That's all. So again, and I keep saying in this course, we walk and then we run. We started with fluid statics, and now we see it's just an isolated or very simple case of the general case of fluids in motion. Here is, I think this was equation 14, but this has the unsteady term dV dt, the convection term v dV dx, and on the right-hand side, pressure gradient and elevation. What if you had a static fluid, so steady state, static, and you're moving only along the x? Well, that would just tell you that dz dx is 0. Again, fluid statics is just a subset of what we just derived from moving fluids. So, in general, V is a constant irrespective of the particle path. So what we said was we looked at the x direction and we said d dx of v squared over 2g plus p over gamma plus z is equal to 0. Therefore, v squared over 2g plus p over gamma plus z is some constant. Now, what we can do is liberate ourselves of the need of worrying about where we are. We can just say that the x direction is wherever our main direction of flow is. So if we're looking at a piping system that moves in different directions, x can just be the direction we're looking at. How can we do that? Because z is built into this system. How convenient. And if you think of a pipe again, x is in the direction of flow, y and z, well, there's no flow outside of the pipe, right? So we're typically only looking at what's happening in the x direction. And that's the dominant direction of flow. Is there actually velocities or velocity fluctuations in the x and the z? Absolutely. That's what turbulence is. Turbulence is basically a mixture of three-dimensional vortices as the fluid moves. So you always have these components of velocity in the other two directions, but their time average is 0. They just vary about 0. as long as you have the continuum and can draw the path line between 2 points, the Bernoulli sum is a constant for now. Later in the semester, it won't be constant, and I will tell you that day. If the fluid is moving, do not expect fluid statics to be operative. What does that mean? Pressures can now change just due to the velocity itself. So before we said dp dx was 0. That's not true now in a moving fluid. We can have pressure changes, and I'll sketch that for you. We can now have pressure changes in the horizontal direction just because velocity changed. The common example I use you got a $10 bill, 2 5s, and 5 1s. How much money do you have? 10, 2 5s, 5 1s. $25. If I put it all in one pocket, how much money do I have? $25. If I take out a 5 and put it in my shirt pocket, how much money do I have? $25. If I take out the 10 and put it in my other pocket, how much money do I have? $25. You can keep energy as v squared over 2g. You can keep energy as p over gamma. You can keep energy as z. But in a system without mechanical energy, meaning pumps or turbines, the sum is always the same right now. All you do is convert, move from one pocket to another. So you can convert velocity to pressure, et cetera. You've done this hundreds of times. Have you ever taken a balloon after you blew it up and just let go of the end and let it deflate? You're converting p over gamma to v squared over 2g. We do this so often. All I've tried to do is make it so complex you don't even know what it is anymore. But your life experiences have done this all the time. So I want to talk about grade lines. Next semester in, I don't even remember the name of it, the old 645. It's 620 now. In 620, you will be using these. You will be expected to know these. And whoever is teaching that course will ask you about it if I went over it. And just remember, you give them the deer in the headlights look, and you just go like this, because it'll drive the professor nuts, but I do go over this and they know I go over it. So we can calculate at any point in a system the Bernoulli sum. And when we connect that locus of points with a line, that's known as the energy grade line, EGL. And we're going to be doing that in examples. Similarly, the two forms of potential energy are pressure and elevation. The sum of the pressure and elevation terms, P over gamma plus Z, is known as the hydraulic grade line. And through a system, again, we can calculate P over gamma plus Z at any point in the system. And when we connect that locus of points with a line, that's called the hydraulic grade line. When you leave here and you do designs of systems where fluids are moving, inevitably, you will have to submit the EGL and the HGL for those designs. You need to show people what it is. They're going to ask for it. So it's not like something we just do in the ivory tower. This is what you have to show. So let's look at something that looks like this. When you draw this, leave space above and below this pipe. So this is a pipe. And flow is from left to right. So we first go into a contraction and then we go into an expansion. So it goes from the original pipe diameter to a smaller pipe diameter back to the original. If we have this discharge, we know that The discharge divided by the cross-sectional area is the velocity. So we would start at the total discharge. It's constant, that's steady flow. At this location, the discharge over A1 would give us velocity V1. The discharge over V2, since discharge over A2, since A2 is smaller than A1, would give us V2. And then when we go back to the original diameter, V1. Is V1 greater or less than V2?
Less than.
Everybody agree? So let's say that we put a manometer here. Should drop a little higher. And the fluid level in the manometer is here. And so at that first location where we have the manometer, we have some pressure P1, and as a pressure head, we would divide by the specific weight of the fluid. So P1 over gamma is the height of that fluid. Since we have some velocity, a distance above that gives us the center line distance. So Z is on the center line of the pipe, and that's where a manometer is reading the pressure. Z plus P over gamma plus V squared over 2G is the Bernoulli sum B. A few slides back, we said that B was equal to a constant, right? D dx of all these terms is 0. So this is the energy grade line. And for our systems right now without mechanical energy, it's a constant. dB dx or dV squared over 2G plus P over gamma plus Z dx is equal to 0. It's a constant. As we move towards the contraction, what's happening to V squared over 2G?
Increases.
It's increasing. So what must be happening is the EGL and the HGL are coming into the contraction, and they need to separate because V squared over 2G is increasing. This is a horizontal section of pipe. Does the center line elevation of the pipe change? Is there a change in the center line pipe elevation? No, dZ dx is 0. So as I increase V squared over 2G, who paid the price? P over gamma. So what happens is, as you move into this, this is, and it's happenstance that it went to the top of the pipe. It can go anywhere. This is V2 squared over 2G. And this distance from the pipe center line to here is P2 over gamma. This could go like this. So depending on how much you constrict that, you can keep driving the pressure lower and lower. Is there a limit to how low the pressure can go? Vapor pressure. So I've made this example before. You take a running hose of fluid, your hose and your garden hose, and you crimp it, and you hear the hissing inside of the hose. What you've done is driven the pressure in the system to below the vapor pressure, and you've cavitated the fluid. Okay. So you actually have a lab on this, and you're playing around with this, but it's just showing you very simply in this system how you can convert from one system of energy to the other. We're moving horizontally, and yet dP dx is not 0. PDX is non-zero because we have changes in where we're storing energy. We're putting energy, we're taking it out of P over gamma, putting it into B squared over 2G in the contraction. And when we go back, we switch it. Okay. We will continue with this next time. We're getting to numerical examples. That's where we're heading. Any questions online before I log on?